Hi Rockridge, this is Mrs. Berger, and today we'll be talking about Introduction to Polynomials. So let's launch into the notes for today. The first thing we want to talk about with polynomials is what it means to have a degree of a polynomial. So the degree of a polynomial is the highest exponent of all the terms in the polynomial. So if you have a degree of 0, that means the highest power of the variable, of all of the variables, is 0. This type of polynomial of a degree of 0 is called a constant. Okay. A degree of 0 polynomial of the standard form looks like this: f of x equals some constant a sub 0. An example of this might be y equals 3x to the 0 power. If you recall, x to the 0, or anything to the 0 power, is 1. So we can simplify this down to y equals 3 times 1, which is y equals 3. 3, of course, is a constant, just like any other a sub 0 term you might find. Y equals 3, that's a constant. And we know from earlier algebra classes that y equals 3 or any other constant looks like this, a horizontal line. So that's a degree of 0 polynomial. A degree of 1 polynomial is called a linear polynomial. The highest degree here of the standard form is 1, and it's usually an invisible 1, but I wrote it in here for you. So an example of this might be y equals 3x plus 2. Okay? See how this x is raised to the 1 power? That's the highest power of any variable in that. And we know that a line like this is what that looks like. A degree of 2, we just spent a lot of time talking about these kinds of polynomials. A degree of 2, that's a quadratic. Quadratic, the standard form is this. See how the highest power on any of the x's here is a 2. An example might be y equals 3x squared plus 2x minus 1. Please note that even though I've written 3 terms here, you don't necessarily have to have all 3 terms of the standard form to still qualify as a quadratic. Y equals 3x squared is also a quadratic. It's just missing these last 2 terms, the linear and the constant. And we know from our last couple of units that these look like this, a parabola. A degree of 3 is called a cubic. This is the standard form here. See how the highest power is a 3. An example might be y equals 3x cubed plus 2x. And I'm just going to leave it at that just to show you that this is still a cubic function, even though we have a linear term here and no other terms. Since the highest power is 3, that's the cubic function. If you remember correctly, this is a cubic. That's what a cubic looks like. A degree of 4 is called a quartic. The highest power is 4. And we can have any number of terms in here. Let's make 3x to the 4th minus 2x squared plus 5. It really doesn't matter as long as the highest power is a 4. That's a quartic. Quartics look like this, and we'll explore that a little more later in the lesson, but that's what those look like. Now, just because we've only talked about degrees 0, 1, 2, 3, and 4, that doesn't mean that there aren't more. You could have a degree of 156. I don't know what the name of that is. I don't know what we call a degree of 156, but you could have any degree. The degree of the polynomial is just whatever the highest power is on the variable. Now, if you recall, when we were talking about is it a function, is it not a function, we used something called the vertical line test, or we looked at the set of values in the domain and made sure that they didn't repeat. Another way we can look at this is if we're looking at these polynomials, how do we know if it's a polynomial function? We say, are all the variables raised to a power of a whole number? All variables raised to whole number powers. So let's look at some examples and see if we can tell if they are in fact polynomial functions. If we look at number 1, let's answer the question, is it a polynomial? We have x to the 2 here, x to the 4 here, and an invisible little x to the 0 here, right? That's the constant. The highest power I see on a variable here is 4, and I don't see anything that's not a whole number power, so I can declare yes, this is a polynomial, and the type of polynomial is a quartic. Even though these terms are not in order, the highest power is not the first one listed, we go choose the one that's the highest power in the list. And that highest power is 4, so we're going to call this a quartic function, even though the terms aren't in the right order. The next one has x to the third power plus 3 to the x power. X to the third power leads us to believe that this is a cubic, but when we go to the 3 raised to the x power, this automatically calls it no for polynomial function, because the x is not a whole number power. Nothing raised to the x power could be called a polynomial function. Similarly, number 3, we've got a quadratic power here, and we've got a linear power here, but this one right here is a troublemaker. If you recall from earlier lessons, x to the negative 1 can also be written as 1 over x. Either way, these are not positive whole number powers, and so this one kicks it out of the running for a polynomial function. Number 4, negative 0.5x plus pi x squared minus the square root of 2. We might be hovering over the no button on this one because of all these funky numbers here. But let's look back at what we're looking for. We're looking for the powers on the variables. We're looking for the powers on the x's. This power on the x is an invisible 1. This power on the x is a 2. And this square root of 2 is basically being multiplied by an x to the 0. So this one is actually fine. The coefficients being weird are not the problem. The powers on the x's are what we're looking at. So yes, this is a polynomial, and the highest degree I see is 2. So I'm going to call this a quadratic. That's how we test to see if a polynomial is a function. Now, let's talk about evaluating polynomials. In the past, when we've asked to evaluate f of x at f of 3, we simply plug 3 in for every x and then evaluate. That is what we call direct substitution. We've been using direct substitution all this time, we just didn't know that it was called that. So let's do a little bit of practice on that. Let's evaluate f of 3 by replacing every x with a 3. Now, we use our PEMDAS for order of operations, and we make sure that we bring things to the powers, the exponents, before we do any multiplying, dividing, adding, or subtracting. Let's go ahead and take a moment to evaluate that, and you're welcome to use your calculator, and make sure that you're using the powers and the multiplying and dividing and adding and subtracting orders correctly, and let's see if we come up with the same number. Hopefully after you've had a moment to put that into your calculator, you should have gotten 98 as the solution to f of 3. Again, we just used direct substitution to evaluate that. Let's try it again on number 6. Direct substitution. Enter negative 2 wherever you see an x. Remember, when we bring negative 2 to the 4th power, we should have a positive number. When we bring negative 2 to the 2 power, it should be positive. When we multiply 5 times negative 2, that should be a negative 10, and so on. Order matters on these PEMDAS, on your order of operations, and take care on those negative signs. Go ahead and try to evaluate that. After entering that in the calculator and having a moment to think about it, hopefully you got to negative 17. Again, that was direct substitution. Now we're going to try something called synthetic substitution, which is sometimes quicker and easier for evaluating these. Let's look at f of 3 for this function. I want you to draw this little L-shaped half box, I guess, half rectangle, and put the coefficients of every term in order. And if you're missing a term in the order, I want you to put a placeholder 0. Let me show you what I mean by that. The highest power here is 4, and all the other terms after it are in order. So I'm going to take the coefficient of the x to the 4th power and put it here. Then I'm going to look for the x to the 3rd power. There isn't one in the list. so I'll put a 0 placeholder. Then I'm going to find the coefficient for the x to the 2 power. That's -8. Then I will look for the coefficient for the x to the 1 power. That's +5. Then I'll look for the constant. That's -7. I'm evaluating this function at 3, so I'll put that here. Now, here's how we use this tool for synthetic substitution. Your first coefficient steps down as is. Then we multiply up. We take 3 times 2 and enter it here as 6. Add down. 0 plus 6 is 6. Again, multiply up. 3 times 6 is 18. Add down. -8 plus 18 is +10. Do it again. 3 times 10 is 30. 5 plus 30 is 35. 3 times 35 is 105. -7 plus 105 is 98. Your last number here is your answer, is f of 3. F evaluated at 3. Notice that we actually had the same work up here for f of 3. We had the same answer. Direct substitution and synthetic substitution get you the same answer. Sometimes synthetic is faster. Let's try one more for synthetic. Set up your box. Grab your coefficients. Everyone is listed in order here, so that's good. Your end of the fourth is your highest power. The coefficient on the end of the fourth term is 1. The end to the third term is missing, so we put 0 as a placeholder. N to the 2 is present, n to the 1 is present, and the constant is present. We're evaluating this at -2. Don't forget, the first number is brought down as is. Then we set to the multiplying task. -2 times 1 is -2. 0 plus -2 is -2. -2 times -2 is +4. -5 plus 4 is -1. -2 times -1 is 2. 9 plus 2 is 11. -2 times 11 is -22. 10 plus -22 is -12. -12 is the answer of S evaluated at -2. Let's do one more together, and then I'll give you a moment to check your skills on this in the box. So let's do one more. P of x. Let's set up our synthetic substitution table. Everything seems to be in order, and I actually have a 4, 3, 2, 1, and 0, so I don't need any 0 placeholders. I'm evaluating at 2. I bring the first term down as is. Then I set to multiplying up. 2 times 3 is 6. Add down. Multiply up. Add down. Multiply up. Add down. Multiply up. And add down. P of 2 equals 0. The final item in your list is your answer. Go ahead and pause the video and work on A, B, and C in the You Try section, and then play it to see if your work matches. If you don't get the same answer as I do, go ahead and check and see if you made a negative sign or if you didn't bring the first term down. Those are usually the two things that folks mess up. Go ahead and pause and attempt A, B, and C. Alright, hopefully you tried A, B, and C on your own. Go ahead and check to see if your answers match mine. -14, -16, and -1141. If they don't match, let me suggest looking at a couple of different things. Did you bring the first term down as is? When you multiplied a negative times a negative, did you get a positive? When you multiplied a negative times a positive, did you get a negative? When you added a positive and a negative, did you do it correctly and bring the sign correctly? And also on C, did you have two placeholders? Did you have a placeholder for the x to the 4th term and a placeholder for the x to the 2 term? Hopefully you got it right on the first try, but definitely practice and making the mistakes first are where you learn. So go ahead and spend as much time pausing the video and looking against my work to make sure that you have the concept down. When you're ready, go ahead and move to the next slide, which is end behavior. We talked about end behavior before. Let's fill in this table with some more information about end behavior. Don't forget, linear functions have a degree of 1. We can have two different types of linear functions. We can have linear functions with a positive leading coefficient or a negative leading coefficient. The shape of a linear function, degree 1 with a positive leading coefficient, looks like a rising line. With a negative leading coefficient, a falling line. The number of turns for this is 0, and we'll talk about turns in a moment. I'll explain what I mean by that. Let's talk about the end behavior. We know how to answer these questions already. On the left, as x goes to negative infinity, you have f of x going to negative infinity as well. On the right, positive infinity goes to positive infinity. For a negative leading coefficient line, you have the opposite. It rises on the left and falls on the right. Now let's talk about quadratics. We said quadratics have a degree of 2. The two types of quadratics are positive leading coefficient and negative leading coefficient. Those look like an opening up parabola or an opening down parabola. Quadratics each have one potential turn. And what I mean by that is, right here, where we switch from decreasing to increasing intervals, that's a turn. It turned from increasing to decreasing. Similarly, on the negative leading coefficient, we went from increasing to decreasing. The point at which it turns is called a turn, and quadratics have one of them, potentially have one of them. Now, end behavior. We know about end behavior for quadratics as well. For this one, it's up on the left and up on the right, so the ends match. For this one, it's down on the left and down on the right. Again, the ends match, but they match down, down instead of up, up. We're going to start to see a little pattern forming on some of these things. Let's go to cubic. Cubics have a degree of 3. They can have positive leading coefficients or negative leading coefficients. Cubics look like this for a positive leading coefficient, or they look like this for negative leading coefficient. They have two turns, increasing, decreasing, increasing, or decreasing, increasing, decreasing. They turned twice. Now, on the left side of the positive leading coefficient, I'm approaching negative infinity. And on the right, I'm going to positive infinity. The ends don't match. On the left for the negative leading coefficient, I'm approaching positive infinity. And on the right for the negative leading coefficient, I'm approaching negative infinity. The ends don't match the other way. Let's fill out our table for quartic. Certainly, like I said, there are more than just quartic functions, but this will show us our pattern. For a positive leading coefficient, quartics look like this, of some kind. And they have 3 turns. Turn here, turn here, turn here. For negative leading coefficients, they look like this. Same number of turns, different end behavior. For the quartic, we're up on the left and up on the right. The ends match up. For a negative leading coefficient, they're down on the left and down on the right. The ends match down. That sounds familiar. That's a lot like what happened with quadratics. So, however you need to take these notes, let's talk about some of the patterns that emerge. For even degree polynomials, the ends match, the end behavior matches, and it's up, up, for positive coefficient, positive leading coefficient. And it's down, down for negative leading coefficient. And of course, on a quiz or test, you wouldn't say up, up, or down, down. You'd say as x goes to negative infinity, f of x goes to positive infinity, etc. Just for our notes to get the concept down, I'm just saying up, up, down, down. Now, for odd degree, linear, cubic, to the 5th power, to the 7th power, to the 157th power, the ends don't match. Ends don't match. They are down on the left, up on the right for positive leading coefficient, and they're up on the left, down on the right for negative leading coefficient. That one's harder for me to remember, so what I try to remember is, how do lines work? If I have a positive leading coefficient on a line, which is a degree of 1, that looks like this. Down on the left, up on the right. The behavior of the ends on the left and right for a degree of 1 are the same as degree of 3, degree of 5, and any other odd degree. So whenever I'm thinking, let's say x to the 7th, that's got to act like a line. And if it's a positive invisible 1 here, it's down this way, up this way, with 6 turns in between. Now the opposite is true for a negative leading coefficient. That's a negative slope line. So if I had, I don't know, x to the 157th, and it had a negative 2 in front of it, or any other negative leading coefficient, I know that it's up on the left and down on the right, just like a negative sloped line of an odd degree of 1. If you need to write more notes to yourself to help you remember those patterns, go right ahead, but that's really what we need you to get out of this, so that when you look at polynomials, all you need to find is the degree and the leading coefficient. Let's talk a little bit about multiplicity. The multiplicity of a root r is the number of times that x minus r is a factor of the polynomial. We've talked about factors versus zeros before. This root here, a, has an odd multiplicity. It crosses this axis and goes straight through. It doesn't bounce. This root b has an even multiplicity. So the factor that might have caused that might have been x minus b squared. This has a multiplicity of 2, or some other even multiplicity. Bounces have even multiplicity, or even powers on the factors. Cross-throughs have odd multiplicity. Let's look at some examples. So for this here, let's talk about how these factors turn into zeros. This factor x minus 1 means we have a 0 of 1. This x minus 3 factor means I have a 0 of 3. The multiplicity of the 1, 0, is 2. This has a multiplicity of 2. The multiplicity of x minus 3, or the 0 of 3, the multiplicity of that is 1. So we have two zeros. One of them crosses the x-axis. That's this one, the 3. One of them bounces at the x-axis. That's the one that has the even multiplicity. That's the 0 of 1 that has the bounce. Sorry, that's a 1. Let's look at the second example. We have a couple of different zeros here. This factor means we have a 0 of negative 2. This factor means we have a 0 of 3. The multiplicity of the first 0 is 2. The multiplicity of this 0 is 2. We have two zeros again. We don't have any that cross the x-axis. They're both even, so we have none that cross at the x-axis. And we have 2, both negative 2 and 3, bounce at the x-axis. Now the last example is interesting. How many x-intercepts do we have? How many zeros do we have? Some of you might immediately say, well, we have a 0 of 3, and we have a 0 of -2, and you would be right. But don't forget, this is also a factor. This is also going to cause a 0. It's going to cause a 0 of 0. So we have 3 zeros. The first 0 has a degree of 1, or a multiplicity of 1. The second 0 has a multiplicity of 1. And the third 0 has a multiplicity of 1. So, we have 0, 3, and -2 crossing the x-axis, and we have none bouncing at the x-axis. That's multiplicity. Let's talk about end behavior, just based on the leading coefficient and the degree of the polynomial. The degree of this is 3, the highest degree, 3. The leading coefficient of that x to the 3 term is -3. I have an odd degree and a negative leading coefficient. So I know that this thing is acting like a line, and it's acting like a falling line, a negative slope line. So I write my end behavior as x goes to -infinity, g of x goes to +infinity. As x goes to +infinity, g of x goes to -infinity. It just has, instead of a straight line, it just has a little turn. 2 turns, actually. 1, 2. Let's look at p of x. My leading coefficient, everyone looks to be in order. My highest power is 4, so my degree is 4. And my leading coefficient is negative. It's -5. It's an even polynomial, so I know my ends match. And since I have a negative leading coefficient, they match down, down. And if you'd like to draw the 3 turns in between, you're more than welcome, but all we need to do is state the end behavior. As x goes to -infinity, p of x goes to -infinity. As x goes to +infinity, p of x goes to -infinity as well. Let's look at k of t. K of t has not been quote-unquote foiled out. That's all right. Let's think about what would have happened if we had foiled all of this out. We would have had x plus 2 times x plus 2 times x plus 2 times x minus 7 times x minus 7 times x minus 7. And when we foiled all of that out, we would have had x multiplied by itself 3 plus 3 times. We would have had an x to the 6th by the time we were all done. And there's nothing sitting out front here, and there's nothing tacked to the front of either of these x's, so that invisible coefficient of +1 is still there. So the degree of this polynomial is 6, and the leading coefficient is +1. Well, since this is even, we know the ends match, and since this is positive, we know they match up, up. Up on the left and up on the right, with 5 turns in between that you're more than welcome to sketch out for yourself. But I'm ready to go for my end behavior statement. As x goes to -infinity, I'm sorry, it should be t. As t goes to -infinity, k of t goes to +infinity, up on the left. As t goes to +infinity, k of t goes to +infinity. Let's look at the last example here, h of x. Again, if we were to imagine x plus 3 times x plus 3 times x minus 4, we would end up with an x to the 3 power at some point. And the only other thing being multiplied to the front of those x's is 1/2. Sure, there's a bunch of other terms after it, but this is the only one we care about. We have a degree of 3 and a leading coefficient of positive 1/2. That means we've got something that acts like a line because it's an odd degree, and the type of line it acts like is a rising line, up on the left and down on the right with a couple of turns in between. So as x goes to negative infinity, h of x goes to negative infinity. As x goes to positive infinity, h of x goes to positive infinity. There's my end behavior statement. I would highly recommend doing a quick sketch, at least of the ends, before you write out your end behavior. Now, let's evaluate, and since we need some practice evaluating using synthetic substitution, let's try that on this first one if it makes sense. G of negative 2. What would we have to do here? G of negative 2, if we base our work on this g of x up here, we would build ourselves a table. We've got a 3, 2, 1, 0, so we've got all the coefficients. No need for any placeholder zeros. And we're trying to evaluate that function at negative 2. Let's go ahead and put this to practice. And there we have it, 41. That could have been faster than doing direct substitution by replacing every x with negative 2, especially with all the negatives we have to worry about with the powers. Let's look at number 6. Does it make sense to use synthetic there as well? Looks like it. I can get this done pretty quickly with just the coefficients. I'm putting 2 in. 4, 3, 2, 1, 0. I have every term. I don't need any placeholder zeros. If that went too fast, go ahead and pause the video. Make sure that you can do this synthetic substitution pretty quickly on your own. Make sure that you line everything up. A lot of times, and I do this to myself as well, I get mixed up and I start adding the wrong things together. So leave yourself enough room to make sure that everything adds up and lines up. Alright, that was pretty quick for synthetic substitution on that one. Take a look at number 7. We're trying to evaluate k of t at a value of negative 1. Does synthetic substitution make sense there? Hopefully you thought about it for a moment and thought, I really do not want to FOIL all of that out and get all the coefficients. And I agree with you. I wouldn't do that either. Sometimes it just makes sense to do direct. So let's go ahead and see what happens with that. If we were to enter a negative 1 in, look how quick and easy this would be. Well, negative 1 plus 2, that's 1 to the third. And negative 8 to the third. Hopefully you got negative 512. That was much faster than foiling all of this out and trying to do synthetic substitution. So we're starting to see when we might use one method versus the other. Alright, number 8. Let's take a look at what we have. H of x evaluated at 2. Again, does it make sense to FOIL all of this out and try to do synthetic? Absolutely not. Unless you just love doing foiling, there's no reason. Let's say 1/2 times 2 plus 3 squared times 2 minus 4. That's 1/2. 2 plus 3 is 5. 5 squared, that's 25. Times a negative 2. That's negative 25. Much faster. On the quiz, you will be asked to do synthetic substitution at some points and direct substitution at other points. So make sure you read the directions really clearly and in depth. But there might be a section on there where you're allowed to use any method, and that's when you get to use your decision-making skills to decide what makes sense, what's the fastest way to do this. Alright, go ahead and try your independent practice. If you are using the same independent practice my class is, I would like you to change number 2 on the homework to look like this. It's a little bit better practice for what you'll be seeing in this class. and good luck, and let your teacher know if you need any help.